Hello everyone, let us solve some numericals in this lecture. These numericals are basically the ones which usually come in exams like graduate aptitude test in engineering, that is GATE exam, what we call. So let us solve one problem. The topics is of course signals and systems. That is what we are dealing with right now. So we have a question where we have been given an input-output relationship where y of t is equal to we have this relationship that is given, the integral from t minus t to t, and the input signal we have is x of u, and just a minute, take it to this side. So x of u du. Basically, we have to comment on whether this system is an LTI system or not. LTI is system or not, that is what we have to tell. This problem was asked in GATE 2017. So we need that, we know that basically there are four options given, and we will be asked like the first option would be that the system is a linear system, but it is not a time invariant system. The system is a non-linear system. The second option would be the system is a non-linear system and it is a time invariant system. The third option would be that it is a non-linear system and it is a time invariant system, and so on. We can have various options. Four options are generally there in GATE exam, in any exam mostly. So basically we'll start solving this question. So we have, now we can see that let us express this particular system in this manner. Suppose t of x of t is equal to what we have been given. First, what do we do to check the linear time invariance? So I'm checking the time invariance first. Okay, I'm checking the time invariance first. So time invariance basically signifies that the delay that has been caused in the input, the same delay is reflected in the output or not. Okay. So we express a system in this form, and we have our system that is x of u du, and that is varying from t minus capital T to t. This is basically our system. Now what we do is we basically perform the delay in our input part. So let us say that we take a delay of t naught in the input. So now what we get here, basically our input will be delayed here. So this x of u will become x of u minus t naught. Okay. So let us consider u minus t naught as another dummy variable, that is, let us say u prime, u bar, sorry. So u bar is our u minus t naught. So whenever we take any substitution in the variable here, two things we have to do. The first thing is that we have to change these the limit over the integration, this differential limit. So basically we get du is equal to du bar. And the second thing is that we have to define the new limits. So we can say that the lower limit on the variable u is t minus t. Okay. So I'll write here the lower limit. I'll try to find out the lower limit for u bar will be equal to, the lower limit for u is t minus capital T. So t minus capital T minus t naught. And the upper limit for u bar, that would be, basically we have u bar is equal to u minus t naught, and u, the upper limit on u is t. So we will have simply t here, t minus t naught, basically that is what we get here. So we get the system as this delayed form. We get as, here we get the lower limit is t minus capital T minus t naught, and the upper limit is t minus t naught, and then we have here this x of, here we have u bar and we have du bar. Okay, this is what we are getting after we have performed the delay in the input. Now let us delay the output. So when we do the same delay in the output, what we'll get, so we can see that here u is just a dummy variable, that is over which we are performing the integration. So u is not of use. The real variables here are t that are present in the limits, because y of t will be obtained in the form of these limits only. So basically we will have, when we have y of t is integration from t minus capital T to t. So we will have y of t minus t naught will become t minus t naught minus t to t minus t naught. Simply this will change in simply this manner, and we will get x of u du. So we can see that since u is just a dummy variable, so we can see that both of these expressions are simply equal. Okay. So we have basically y of t is equal to t minus t to t x of u du is a linear time and LTI system. Sorry, this is still not an LTI system. It's a time invariant system. Now we have to check about the linearity of this system. Okay. So for checking the linearity, what do we do? Basically, we have, when I'll write it again, our y of t that is equal to integration from t minus capital T to t, and then we have x of u du. So how do we check the linearity of the system? We basically give the first input. There are various ways of writing. I'll write in a particular manner. Let us say that the output y1 of t that is equal to the output for the input x1 we are having. So we have x1 u du, and this is varying from t minus t to t. Okay, and then we have y2 t. So that is basically the output for the second input. So we have x2 u du, and this varies from t minus capital T to t. Okay, now we basically sum this output. So what do we get? We can see that we get t minus integration from t minus t to t, x1 of u du, plus we get here t minus t to t, x2 u du. The second thing we will check is that what is the output that we will obtain for a combined input x1 plus x2. So I'll write it in the manner with the notation. I'll write it here y1 plus 2, let us say. That is essentially the output that is obtained when the combined input x1 plus x2 is given to the same system. So we have y1 plus 2 I am writing. That is essentially the output that is obtained when the combined input, that is x1 plus x2, this combined input is given to the same system here, and that is varying from t minus t to t. So we can see that y1 plus 2, both of them are equal. y1 plus 2 is equal to y1 plus, this is y2, y2. So we get y1 plus 2t is equal to y1t plus y2t, which shows that this particular system is an additive system. This is an additive system, and for checking the homogeneity of the system, we can see that we have y of, I'll write here separately, checking the homogeneity checking the homogeneity of the system. You basically can see that, suppose if I'm having, I multiply the input with a constant, let us say that constant is C. So we get the output, the system output that is obtained is, let's say that basically we are multiplying the input here with C, let us say, so that we write it as, let us say in the initial form only we had written it as x, or in the function in the form p of x of p, that is equal to, so here we are basically multiplying a constant term with the input of the system. So we can say that, we can see here that from t minus t to t, we obtain here, after multiplying input with a constant C, that is what we call as scaling. Next is we basically scale the output. So when we scale the output here, that is basically Cy of t. So we can see here that we will get here the C is multiplied there to this integration, and since it is a constant, it will move inside the integral only, and we will get here t minus 2 to t integration. We can see that multiplication of this scalar with the output and multiplication of this scalar with the input gives a same output to us. So both of them are also equal. So this is also a linear system. So essentially, this particular problem can be seen that it is an LTI system. Okay. Then let us have another problem. Suppose we have been given, I'm being asked to calculate, we have been given a signal like in this manner, which I'm going to draw. This is basically, we have x of p is the given signal. This is a parallel line to the horizontal axis, and we have here -1. This is basically x of p. And in this question, this waveform has been given, and we are asked to find the even and odd components or parts of a unit step signal. Okay, u of t. So that in terms of x of t. In terms of x of t. This problem was asked in GATE 2005. Okay, so let us solve this problem also. So we can see that whenever we want to calculate the even and odd part of a signal, we have to do certain operation. Let us say that our unit step signal is u of t. Okay, so the even part of this u of t will be equal to u of t plus u of minus t divided by 2. And the odd part, that is this is a even part of unit step signal Suppose we want to calculate the odd part of unit step signal. So u of t, let us represented by that. That is equal to u of t minus u of minus t by 2. This is the odd part of the unit step signal. Okay. So now we have u of t. Let us draw how u of t looks like. So we know that u of t we have this u of t, this kind of u of t signal we have. If I calculate the time reversed unit step signal, what it will be? It will be drawn in this manner. This is basically u of minus t, and here the value is 1.0. This is varying with time. This is also varying with time, and here it is 1.0 constant value. So if I try to calculate u of t plus u of minus t, okay, so what I'll get is, I'll get a simple constant value, that is u of t plus u of minus t, and here the value will be 1.0. If I want to calculate u of t plus u of minus t by 2, so that the signal will be having this constant value, and here it will be 1 by 2. Okay, so u of t, that is basically the even part of our unit step signal. Okay, so the even part of the unit step signal, u of t, u of t, that will be simply 1 by 2. Now let us try to calculate the odd part of the signal. So for the odd part of the unit step signal, what we do is we have to take the negative of, we already have u of minus t, we have to take the negative of u of minus t. So negative of u of minus t, what it will be? Here it will be like this. Here it is minus 1. This is 0, and we have time varying here. So now when I try to find out u of t, this one here, this one is 1. This is the second waveform. This is the third waveform. When I try to add the first and the third waveforms, so what I'll get is adding 1 and 3. So what I'll get is, I'll simply get here this kind of waveform where this value is minus 1.0 and this value is 1.0. This is varying with time, and the y-axis is basically u of t minus u of minus t. Okay, so when I try to calculate now from this, when I want to calculate u of t minus u of minus t by 2, so what that will be? That will give me, I'm drawing the waveform here, that waveform will be simply the same pattern it will follow. The only thing is that here we'll have 1 by 2 and here we'll have minus 1 by 2. And this is varying with time. And we can see that if we try to compare this x of t waveform that has been given, so we can see that this is essentially our odd part of the unit step signal, and the odd part of unit step signal, that is u of t, that is essentially nothing but x of p by 2, because we are simply, this is essentially x of p. So when we want to find out the odd part of the signal, we will get it as x of p by 2. Okay. So let us take another problem. Suppose I have been given a impulse response in the discrete system, and I have been asked that this particular impulse response which I am going to write, this is the impulse response un plus 3 plus un minus 2 minus 2 un minus 7. Okay, now this particular impulse response, this particular impulse response is represents a causal system or a stable system. We have to basically comment on the causality and stability of the system represented by h of n. Okay, so the first thing that we can see here is that basically if we start talking about the causality of the system, so we can see that this particular system is depending on the future input and the past input and the past input. So definitely it is an anti-causal system. So this is an anti-causal system. Next comes the stability. So for stability, the condition, as you must be knowing, the condition for stability is what? That is basically we take the summation of Hn from minus infinity to infinity, and that should lie within infinity. That should lie within finite limits. It should have a finite value. The summation of h of n should have finite value. So if I simply we need to draw the waveform for u of n plus 3. Next we know the waveform for u of n. The waveform for u of n, we have n on the horizontal axis and u of n on the vertical axis, and u of n is represented by this particular function and so on. This is n is equal to 0, 1, 2, 3, 4, 5 and so on. So we need to delay this, we need to advance this by 3 time samples, the same waveform. Then we need to delay this by 2 samples, and then we need to multiply with 2. First we need to delay it with 7 samples, and then we need to multiply it with 2, and then we need to sum all 3 of them. So the output that will be obtained, that is u of n plus 3. I'm not drawing all of them, otherwise it will become very lengthy. I leave it to you for your homework to draw all the waveforms, and u of n plus 3, and then u of n minus 2, and then first you need to draw u of n plus 3, then you need to draw u of n minus 2, sum both of them. Then you need to draw u of n minus 7 and just multiply it by 2, and whatever comes out you have to subtract it from this added sum, whatever you have obtained. So the output that will be obtained here, I'm drawing here. This is basically our summation from n is equal to minus infinity to infinity. That is what we are doing. That is what we are doing. We are doing basically, we are summing it over this. Okay, and n is equal to minus infinity to infinity. That is what we are doing. So we'll get here the sample points minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, and 6. Here we'll get these sample waveforms. These will be having value 1. Up to 1 we are having here. This has 1.0. And then from 2, we have this only up to 6. Here the values will be 2.0. This will be having a 2.0 value. This will be having value 2.0, 2.0, 2.0, and rest all will be 0. The rest all will cancel out here. So we can see that this summation, this value is a bounded signal. This is basically the summation that is coming out has a finite value, and therefore it is as summation over h of n has a finite value. Okay. Hn represents a stable system. So essentially, we have this particular system is a is a non-causal and stable system. Okay, this particular system is a non-causal and stable system. So that's all for today. We'll solve some more questions in the next class. Thank you.